Hello. On Thursday last week, we did not quite finish all of section 2.4. So today, I'll talk a little bit more about 2.4. And then the next video will cover section 3.1. Recall from last class that if f of x is equal to x squared, f prime of 2 was equal to 4. Okay, we found this last time on the front of that handout for sections 2.3 and 2.4. Today, let's do another one of these, and then we'll move on. Let's try to find f prime of 3. So, from our definition of a derivative, the derivative of the function f at 3, f prime of 3, is the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. Okay, so here I'm using the derivative formula with a equal to 3. Like we've seen a bunch of times now, to evaluate the numerator, I need to plug 3 plus h into the function f of x equals x squared, and then I will also have to plug 3 into that same function. Okay, that becomes the limit as h goes to 0 of the quantity 3 plus h squared minus 3 squared all over h. To evaluate this limit, like we did the other day, I should FOIL 3 plus h and then continue simplifying. So that's the limit as h goes to 0 of 9 plus 6h plus h squared from FOILing minus 9, all divided by h. In the numerator, we see that the 9's cancel. Then I see that each term that remains has an h in common. You can factor out that h in the numerator. That would leave you with 6 plus h. In the denominator, I also have an h. So here now the h's cancel in the numerator and denominator. And at this point, I can just plug in to get the value of the limit. I get 6 plus 0, or 6, for the value of the limit. All right, so here, okay, I know f prime of 2 is 4. I know that f prime of 3 is equal to 6. If you were to do another one of these examples, right, you could do a similar thing and find that f prime of 4 is equal to 8. And pretty soon you'll start to notice that the value of the derivative of f of x equals x squared at any given location is just 2 times the input. And so here in section 2.4 we're changing our interpretation. At first, a derivative was defined to be a number, okay, to be the slope of the tangent line at a given point, to be the instantaneous rate of change at a given instant. But if we change that instant, right, if we go from 2 to 3, or from 3 to 4, or if we try to think about the instantaneous rate of change at any other value, likely that rate will be different. And so now we want to think about f prime of x as a function. Okay, in other words, I want to let the input to the derivative here vary, okay, and start to explore what sort of information f prime of x as a function has, or what it can tell me about the original function f of x. All right, the definition on your handout, I'll write it again here, just for fun, is f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h, if it exists. So in this example, for f of x equals x squared, let's go ahead and find f prime of x as a function. It's the same definition as before, limit as h goes to 0, of f of x plus h minus f of x over h. But now instead of plugging in like h plus 3 or h plus 2, I'm plugging in h plus x at first, and then I'm plugging in x for the second term in the numerator. It looks like this. The limit as h goes to 0, quantity x plus h squared minus x squared all over h. I simplified just like a minute ago. I have to FOIL the x plus h in the numerator. That gives us the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. Just like a second ago, I see that my x squareds cancel. Now I see that each term in the numerator has an h in common, so you can factor it out. You get the limit as h goes to 0 of h times 2x plus h from factoring, all divided by h. At this point, the h's cancel, like they did before, And now I can plug in h equals 0 to get the limit. So I get 2x plus 0, or just 2x. And so what we're seeing is that if the function is f of x equals x squared, its derivative as a function, f prime of x, is equal to 2x. And this agrees with what we saw a moment ago. So now, right, if I want to know f prime of 2, all that I have to do, if I have this formula for the derivative, is plug in x equals 2. Right? And so that would be 2 times 2, and that would equal 4. That matches up with what we saw on Thursday. Right? Or I could do f prime of 3. That would turn out to be 2 times 3, or 6, like I just did in a longer calculation on the other board. Okay, so from here on out, it's going to be very useful for us to think about the derivative as a function itself. Here's an example of something that we should be able to do. This is 2.4 number 4. I want to sketch a graph of f prime of x, right? If I have a function of x, it's often useful to know what its graph looks like. So here I'm going to try to sketch f prime given a graph of f. And I'll just make a real rough sketch. Right? So here's my graph of y equals f of x. And somehow, right underneath this, on another coordinate axis, I'm going to try to sketch f prime down here. How do I do this? Well, I know, what do I know about the derivative? Right? I know that f prime of x, or f prime, tells me about the slope of the tangent line, and it also gives me the instantaneous rate of change at a given location. And so, at any given x, if I plug in a particular x value, f prime tells me the slope of the tangent line at that location, or we can think about it as really being sort of the slope of the curve at that location. So when we look at the graph of f here, to me there are three locations that really stick out. And those locations are these kind of places where the curve flattens out. Like right here, right, the curve kind of flattens out, and I would have a horizontal tangent line there. Up at the top, in this location, it looks like I also have a horizontal tangent line. Same thing for right here. If I have a horizontal line, well, this one doesn't work that well either, but if I have a horizontal line, I know that the slope is 0. Well, since I'm talking about tangent lines here, if the slopes of those are 0, that would mean that f prime is equal to 0 at those 3 locations. Right? So coming down to our other picture here, the derivative will have a value of 0. Right? So it'll have a dot on the x-axis at all 3 of these spots, because the slope is 0 at these locations, right? F prime equals 0, f prime equals 0, f prime equals 0. And so those dots on the x-axis are at a height of 0 for the derivative. What else can we say? In this region right here, right, it looks like from minus infinity to wherever this little minimum is right here, my function f seems to be going down, seems to be decreasing. And like we talked about on Thursday, if the function is decreasing, we would expect the derivative to be negative. We can see this if we think about slopes as well, right? Any tangent line in this region over here will have a negative slope. And so that translates down into my graph of the derivative, because the derivative will have to be negative in this region. Right? And we can say a little bit more even, right? It looks like the derivative, the slope is pretty steep here, and then it starts to get less steep. And if it's negative and it's getting less steep, that would mean that it's getting closer to 0. So it starts kind of really negative, but then it gets closer to 0 as it gets less steep. Okay, in this region right here, what's going on with the function? Well, the function is increasing. Right? F is increasing, which would mean that my derivative is positive. And so after the derivative is 0, now it's positive, right? So it comes up above the x-axis, it's positive. But as I get closer to the top, it seems to be getting less positive. It seems to be flattening out. The tangent lines seem to be flattening out or getting closer to a value of 0. So my derivative value comes back to 0 here. In this next little region, right here, what's going on with the curve? The curve is is decreasing. And so, like a moment ago, when the curve is decreasing, the derivative is negative. So my derivative becomes negative here, below the x-axis. But it flattens out again, right? So yes, it's negative, but then it gets closer and closer to 0 again because the slope is getting closer to 0. And then for the last part, over in this sort of final region here, f is increasing, the function is increasing again, and all of the slopes of the tangent lines here are positive. And so the derivative has to be positive over here. Okay, I'm not really worrying at this point too much about how quickly my derivative is growing, or maybe does it flatten out here, I don't really know at this point. But this gives me a rough sketch of the derivative. And I get this sketch of the derivative just by thinking about slopes of tangent lines at various locations. Some other material in 2.4 I want to talk about. We're going to save a little bit of it for a later section, but as just a quick note, there are some alternative notations for the derivative. Okay, our notation, right, so let's say that our function is y equals f of x. The notation that I have for the derivative right now is f prime of x. This is notation that we've been using all along. An alternative notation, which is also very common, is dy dx. As I mentioned in the book, dy dx is called Leibniz notation, after Leibniz, who was one of the founders of calculus along with Newton. Some other notation that you might see, although it's less common, I probably won't use it that much in this class, is capital df. Or you might see capital dx, d sub x of f. You might also see d dx of f of x. Okay, any of these expressions can be used to represent the derivative of the function f. They also talk about how we might use other letters when we're talking about derivatives. Just like we do when we're talking about functions, right? If we're talking about cost, it makes sense to use the letter C for cost. If we're talking about, in this next example, we're talking about knowledge, and we're going to use capital K for that particular function. So kind of quickly here, I want us to think about 2.4, number 49. We're given a function, capital K of t, and we're told that it's a measure of the knowledge that we gain by studying for a test for t hours. Okay, so here capital K is the dependent variable, lowercase t is the independent variable, standing for time. And then I'm supposed to somehow decide which is larger, k of 8 minus k of 7, or k of 3 minus k of 2. There are many ways we can think about this and answer the question. I'm going to try to somehow come up with a rough sketch of what I would expect the graph of k of t to look like. And so here's my t, k axes. What happens when we study for a test? Well, we start to study, And so maybe we have some knowledge without even studying at all. But as we study, we start to hopefully gain more knowledge, right? So we would expect the knowledge to increase. I guess it might keep increasing forever, right? If we could somehow study for a long, long time, for 100 hours, maybe we'll keep learning things. But probably the amount that we learn is going to sort of slow down, right? If we study for 8 hours straight, by the end of that time, we're probably exhausted and we're probably not acquiring all that much knowledge. But at first, we probably learn quite a bit. So I think that the graph of k of t probably should look something like this, where it kind of levels out in the long run. Right, my productivity probably becomes less and less the longer I study. All right, so here's a graph of k of t, a rough sketch of k of t. And now I need to decide, like the question says, I need to decide which is larger, k of 8 minus k of 7 or k of 3 minus k of 2. Well, let me put those independent variable values on here somewhere, right? Here's 2, here's 3, 4, 5, 6, 7, 8. All right, and to measure the differences of those outputs, I need to subtract, right? So let's take a look. Here's k of 2, here's k of 3, roughly. Over here, right, we have a height of k of 7. Where's that? Right about there, maybe. And k of 8. Ooh, it isn't really all that much higher, right? Here's k of 8. And so on the y-axis or the k-axis, if we just look at the spacing between the two sets of values that we have here, right, this amount is the amount k of 3 minus k of 2, and this amount up here, which is a smaller amount, is k of 8 minus k of 7. And so I think it would be appropriate to think that k of 3 minus k of 2 is greater than k of 8 minus k of 7. All right, and so why did this happen? Well, this happened because we decided that we kind of acquired more knowledge earlier on when we study than when we do later on. And so our graph has this particular shape. What else can I say about the graph here? Well, because we're thinking about derivatives, right, we decided that we're going to gain more knowledge as time goes on, and so we expect this function k to be increasing. And like I pointed out now, k prime, the derivative, is what? K prime is positive here, right? Slopes of the tangent lines at any of these points are positive, okay? If we want, we can use alternative notation. Instead of k prime of t, I might say dk dt is greater than 0, okay? This is coming back to the fact that I don't need to use f and x as my letters. Another thing to notice here, and this is something that they point out in 2.4 and something that we'll deal with quite a bit more in the future, is that because, right, the curve is flattening out, what's going on with the slopes of the tangent lines? Right, at first the slopes of the tangent lines are fairly large, but then they are getting less steep, right? And so what does that mean? That means that the derivative dk dt itself as a function is decreasing. Right? We're thinking about the derivative as a function now. And like I said, right, the slope is getting less. In other words, the derivative is decreasing. In 2.4, they talk about something called second derivatives, which are, like it sounds like, the derivative of the first derivative, or two derivatives of the original function. And so I'll write it down and then I'll say more about it at some other time. But if my derivative as a function is decreasing, then its derivative is negative. And the derivative of the first derivative is the second derivative, right? And so with the notation from the book, d squared k dt squared is negative, right? And what that means, this notation d squared k dt squared, I could write it like this. I could write k double prime of t is negative, okay? Or we could write it some other way with some other notation. When k double prime of t is negative, that tells me that the original function k is concave down. Okay, in section 2.4 you should have read about concavity. Concave down essentially means that the curve is sort of upside down. On the other hand, if your curve looks like this, that would be concave up. I think about concave up as being like a cup, so that it holds water. Again, we'll talk about concavity more as we go on.